So the lesson for today is on the fundamental theorem of algebra. We're going to learn about the number of solutions in a polynomial function, and we're going to know and apply the conjugate theorems. So let's start off with the fundamental theorem of algebra. What it states is that a polynomial function of degree n has exactly n solutions for f of x is equal to 0. Counting repeated solutions. Now the solutions can be real, they can be complex numbers, but no matter what, there are n solutions when the degree is n. Remember, solutions, we had other words for that. If there are n solutions, there are also n zeros, there are n factors, and this is a new concept, this idea of a repeated solution. A repeated solution would look like this in factored form. We have f of x is equal to x minus 4 quantity cubed times x plus 2. In this case, the factor x minus 4 is a repeated factor. In expanded form, there are 1, 2, 3 zeros that are all the same. All these zeros are at the number, or the x equals 4. So we have 3 zeros at x is equal to 4 and 1 zero at x is equal to negative 2. Altogether, 4 factors, 4 zeros, 4 solutions for this polynomial function. So some very simple questions, very simple examples. How many solutions does the equation 3x to the 5th plus 2x cubed plus x squared plus 10x have? And all we need to do is look at the highest order term. We look at the degree of it. The degree is 5. Therefore, there are 5 solutions. And again, these solutions may not all be real numbers. They could be complex solutions. How many zeros are in f of x above? That's the same thing, because zeros are the same things as solutions. They're the same thing as factors. So again, there are 5 zeros. So the fundamental theorem of algebra is actually quite simple. A quadratic formula, for example, will have 2 zeros. A linear equation, y is equal to 3mx, or 3x plus 2, will have 1 zero. Let's look at zero behaviors, and actually let's be more specific, real zero behaviors. On a graph, a function may look like this. It might, curve up and go up into infinity. We can observe here, when it crosses the x-axis, we have what we call our zeros. We have 2 zeros shown in this case, and again, we can think of them as zeros and factors and solutions. When it crosses through the x-axis right here, that's one type of behavior. Another type of behavior is where instead of crossing through the x-axis, it's just tangent to it. It goes up and it touches the x-axis and then curves back down again. Or it might come from the top and touch the x-axis and then go back up again. 2 different kinds of what we call zero behaviors. And in the case where it crosses the x-axis, the factor term will look like this. It'll be something like x minus 3 to some odd power, like x minus 3 to the 1st or x minus 3 to the 5th power. On the other hand, if it's tangent to the axis right here, the factor is going to look different. It's going to have even degree on the repeated on the repeated factor, something like x plus 2 to the 4th power. So how would we kind of use this information? If we had a function such as this, let's see how we might graph this based on this information. Let's examine the zeros. The zeros in this case are going to be 3, x minus 3, so 3 is going to be one of our zeros. Negative 5, we invert the 5, so negative 5 and negative 1. These are the zeros of this function. Now let's look at the degrees of each one of them. We have an even degree here too. An odd degree, it's kind of this invisible one. And then we have another even degree. So at x is equal to 3, it's going to be tangent to the axis. At the 0 of x is equal to -5, it's going to cross through. And then at the 0 of -1, it's going to just be tangent again. Let's look at the end behavior now. We got to look at the end behavior to fully figure out how to graph this thing. Our degree in this case is 7. How did we get 7? We have a squared term here, plus another 1 here, that's 3, plus another 4 here, that's 7. 2 plus 1 plus 4 is equal to 7. We have an odd degree polynomial, and the leading coefficient right here is 3, and so it's greater than 0, and so from what we learned before, we will have an end behavior that starts off somewhere down here, comes up, bounces around, and goes up through here. So now that we know the end behavior, we can start our graph down below here. It's going to come up through the -5, and it crosses through there, and then as it goes to the -1, it's just going to go tangent to it, because we see that it's even over here. It's going to go tangent to it, come back up again, come back down again, and it'll be tangent to the 0 at 3, and then it will go up. It'll look something like this. And again, these arrows here shows the behaviors. We have an odd degree here, so it crosses through the 0, and then in these other two 0 cases, they're tangent to the x-axis because the exponents are even. I have an example here. You can try it out on your own. Well, you can do it later. Let's go to the last concept. The last concept is the conjugate theorem, and it's a simple theorem that states this. If one of the zeros is, in this example, a complex number, if we know that a plus bi is one of the zeros, then for sure the conjugate is also a 0. a minus bi is a 0 as well. And that also applies if the 0 is a real number with a radical. A plus square root of b, then a minus square root of b is also a 0 as well. So we can apply this property in the following way. Suppose we had this problem statement. Write a polynomial function with the following zeros here. 1, 3, and 5 minus 2i, and also with the leading coefficient of 3. Now there's many different polynomial functions that we can write of this type, but here's one example. Now because we know that 5 minus 2i is one of the zeros, by the conjugate theorem we also know that the conjugate is also one of the other zeros, so we can say that the other zero is 5 plus 2i, the conjugate of 5 minus 2i. So based on these 4 different zeros, we can write a function f of x with the leading coefficient of 3, so we write 3 right here. And then we can write all the different factor terms like this. We have a 0 at 1, so we write x minus 1. We have a 0 at 3, so we write x minus 3. And then we have a 0 at this number 5 minus 2i, so we write that down, x minus 5 minus 2i. And x minus our last 0, 5 plus 2i. So this is actually an expression. We could almost think of it like the intercept form when we had the quadratic. This is a way of writing out the polynomial function knowing all the zeros. We can then do some manipulation of this and expand it. I won't go through all the details of the math here, but I'll just kind of display this for you to see how this can be simplified down to a single standard form polynomial, a 4th order polynomial with the leading coefficient of 3 and the zeros as specified in the problem. That's it for the lesson for today. Have a good day.